So the next topic in your unit 4, subject surveying 2, is geodetic survey. Okay, so the books that I have referred for this is Surveying Volume 2 by Bispoon and Surveying Volume 2 by S.K. Dugal. Also, I have referred another book which is available on Civil Engineering Books app, that is Surveying by A.M. Chandra. Alright, now let's understand what this geodetic surveying means. So geodetic surveying is primarily the surveying which takes into account the curvature of Earth. So if you remember when we did our, let's say when we were studying our leveling. So let's say if I have to find out, this is my staff station, okay, and I'm given my benchmark here, okay, and I'm asked to find RL of this point. So how do I find it? I have the benchmark plus I add this my backside, okay, so I get the elevation RL of height of instrument, and then I deduct my foreside, I get the RL of the staff station. Now over here, what happens if this thing is this profile? I'm just assuming the reference line is a straight line. Everything is with respect to this. I'm deducting or adding something to this horizontal line. But the fact is, this horizontal line, when you're when your points are over large distance, is not always horizontal. Correct? It's not always horizontal. It will eventually get refracted, or it will have some atmospheric refraction. So that is one thing. Now, always we realize that our datum is mean sea level. Correct? Now, when I say mean sea level, it's not a horizontal surface. Our Earth is a circle, right? And mean sea level will also be a circular surface. Correct? We always assume the level of water everywhere, of course, apart from the tidal variation. We assume that the mean sea level is going to be a constant level, but then that constant level is not a horizontal level, right? It's a curved level. So when I'm trying to add or subtract, okay, when I have this point and I have another point, okay, and I'm adding and subtracting from a horizontal point, okay, it should be actually ideally like this. 1 point here, 1 point here. So now, whatever we did for such a case is not valid over here. Are you understanding? Yet again, then we do not consider the visibility also. Some places, the point is here, another point is here. Now theoretically, let's say there is a point 1 meter above the mean sea level and another point 1 meter above mean sea level. In case of plane surveying, what happens? It will obviously be visible, right? If it's visible from, if this point is visible from my instrument station, then this point also should be invisible from my instrument station. However, when the distance increases, okay, and when the curvature takes into place, if my instrument station is here, just because this one is visible doesn't mean this one also will be visible, because my horizon comes into picture. Right? So all these issues will arise. Obviously, they will not arise when you are doing your practicals. They will not arise when you are doing a survey for small area. They will arise when you are doing survey for large areas. Okay. So when we are carrying out surveying, performing surveying operations on areas which are greater than 250 square kilometers or 12 kilometers in length. Okay, if it's a route survey which is having the distance between the 2 points more than 12 kilometers, or if it's an area survey wherein the area is around more than 250 square kilometers, then you will have to take into account the curvature of Earth, which we are going to study in this particular chapter. Okay, now who conducts this kind of surveys? This kind of surveys will be conducted by national bodies, national survey departments. Obviously, the precision level in this kind of survey is very high. So also the instruments that will be used in this kind of survey will be of much higher order. You usually go for techniques or technologies which are way better than the ones we use for our normal plane surveys. You will go for more refined instruments. Okay, the signals that will be captured, okay, will be either using electronic devices or also technologies like GPS or remote sensing or GIS. This kind of technologies will be used. Right? What is the objective of geodetic survey? The primary objective of geodetic survey is to determine precise position of distant points on the surface of Earth. Now, these points will be far apart. The other objectives is to get reconnaissance. Reconnaissance is the when you go on a site, the first information that you get. Okay, that's called reconnaissance information and primary data required by engineers while selecting suitable routes and sites. The importance of control points in surveying is that it allows to define the selected location. So basically in the geodetic survey, we will be establishing the primary stations, okay, which will be actually a guiding force for the secondary stations. Geotechnical survey systems guide construction forces by setting stakes or otherwise marking lines, grades, principal points, and giving technical assistance. Okay, it measures construction items in place to prepare progress report. It also carries out dimensioning of structures and for preparation of as-built plans. It detects settlements using pre-installed targets on buildings or structures of pavements or embankments. It can monitor ongoing construction projects 24 by 7. It monitors deformations taking place in structures, buildings, bridges, tunnels. It ensures the safety of nearby assets to the construction land. Right now, Earth as spheroid is the next topic. Now, we all know Earth is not exactly like this. Okay, we'll start with the spheroid and we'll go on correcting. So, when we consider Earth in 3D, there are certain terms that you're expected to know. First is mean sea level. Mean sea level will be a curved surface like this. Okay, and greater circle will be the circle which will be circumscribed by any section of Earth. So if I now this horizontal plane, if I consider the horizontal plane cutting at any point on the Earth along the perimeter, the circle that will be formed is called greater circle. Okay, and if I take any 2 points on this greater circle, the line that joins these 2 points is called a chord of the circle. Okay, now if I select any, now you'll have to visualize this as a 3D surface. Okay, not a 2D, it's not a circle, it's a sphere. So if I take any 3 points on Earth, okay, they will not be connected by 3 lines, they'll be connected by 3 arcs of the circle. So this will be, you'll have to visualize this. Okay, this will be one, sorry, this will be one circle. Okay, like this, there'll be one great circle. Okay, then this will be another great circle, and then this will be another third one great circle. Okay, so like this. So now if I take any 3 points, let's say PQR, it's already made. Okay, if I take these 3 points and I join these 3 points, they'll be joined by not 3 lines but 3 arcs of the great circle. That's the reason when I add these interior angles, it will not add up to 180. If it was a triangle, it would add up to 180. Here in this case, this being a spheroidal or spherical triangle, the angles, this R, P and Q angles will add up to more than 180. Okay, so in a geodetic surveying, you are going to consider every line as actually a part of a greater circle. Okay, there are different types of surveys which are conducted in geodetic. We'll go into that depth a bit later. Right, but now again, here also there is an assumption. In reality, Earth is not even a spheroid. It is an ellipsoid. Now, what is an ellipsoid? What is an ellipse? Ellipse is basically a curve which has one axis larger than the other. In case of sphere, what happens? Both the axes are equal. Now, we all know there is a agreement that at north, south, that at the poles, Earth is flattened. Okay, so we have to actually apply corrections in these terms also. So also there is another hypothesis that if I take a cross section here at equator, okay, at equator, if I take a cross section, again that also will not be a circle. That is also supposed to be a little bit of, there is a distortion in that also. That is also supposed to be ellipsoid. But anyway, that is not a part of this particular lecture. So let's go into the details of geodetic surveying. What are the various processes? The first process is astronomic positioning. Then we have triangulation, trilateration, and traverse. Some of these terms are already known to you, some are a bit new. So let's understand what is astronomic positioning. Okay, what is astronomic positioning? This is one of the oldest referencing systems used in surveying. You know, in the ancient times, people used to travel, and their guiding reference was stars, okay, the celestial objects. Right from before, especially the mariners, or now people who are traveling through the aerial medium, they use these astronomical observations for reference. Okay. Explorers have even used astronomical methods to locate themselves in uncharted areas. Geodesists must use astronomic positioning along with the other types of survey data such as triangulation and trilateration to establish precise positioning. Now there can be multiple methods of collecting astronomical data. What is astronomical data? Basically you fix a celestial object. So your reference will be with respect to, let's say, a star or a satellite, something like that. Okay. Now it can be a natural satellite or it can be a man-made satellite. Measurement by determining the difference in hours and minutes and seconds between the time specific star which is directly over the Greenwich meridian and the time the same star is directly over the meridian plane of the point. Okay, that is called astronomic positioning. Short wave radio equipment is used to obtain the time signals. Can you give me an example of short wave radio equipment? Basically, we are talking about GPS, which we have just recently covered. Right. Now, let's go to the slide. There are three terms, some of which you people have already used. Triangulation, trilateration, and traverse. What is the difference between all these three terms? Many a times they always come together. Triangulation, trilateration. What is the actual difference between triangulation and trilateration? You look at these images. Okay. Here in this image, there is a network of triangles and the observations which are recorded are marked. Can you see? What are the observations? Observations are basically the angles. So in triangulation, we measure the unknown distances by establishing a baseline length. I have to edit it through angle measurement. Okay, so over here you can see this. Can you see this? So what you're doing, you have 3 points, you're measuring the angles. And using these angle measurements, you are actually determining the unknown distances. The equipments used here will be theodolite or any electronic distance measuring devices such as total station. Okay, where the angles will be recorded and the distances will be deduced, it will be calculated. In trilateration, the length of all the sides of triangles, polygons, or quadrilaterals, or whatever may be the figure that is formed on the surface, are measured with electronic instruments or any other different recent technology. The angles are then computed from the field measurement. Okay, so this is a bit advanced technique. Traverse. Now, what is a traverse? Traverse is a series of connected lines whose lengths and in triangulation we have measurements of angles, whereas in trilateration we have measurements of sides. Okay. Then in triangulation we have baseline measurements. Okay, check baselines are also measured to control the scale error. Intervisibility between the stations is obviously essential. There are more internal checks in comparison with trilateration, and the side lengths are also computed. Whereas in case of trilateration, check angles are measured to control azimuth error. And small areas, it is possible to measure distances without intervisibility. There are less internal checks in comparison with triangulation, and the angles are computed on the basis of measured sides. Fundamentally, in case of geodetic surveying, we are more concerned about triangulation. Why? Because in geodetic survey is mainly established using triangulation, or it's also called precise traverse. Okay, we have a system of interconnected triangles. Okay, there are various guidelines for forming this kind of triangles. Okay, and most of the triangles are on a baseline. Okay, main line is the baseline, and the measurements of angles is done very precisely in case of triangulation. Then, knowing each of the lines and the angles, the lengths of other sides will be measured. It's a basic trigonometrical thing that we learn, right? Now, always the corners of the triangles will be called the triangulation stations. Okay, and if it's a network of multiple triangles, then it's called a triangulation system or triangulation figure. The triangulation surveys are primarily carried out for fixing the control station, okay, or the control points. It gives you a better precise method of surveying. Okay, it's also used in photogrammetric survey. What is a photogrammetric survey? Wherein you are actually making use of the images which are collected from different platforms for studies. Okay, so if you collect images from platforms, again the ground validation is required. So you have to establish ground stations. So basically triangulation will be carried out in order to establish these ground stations. Okay, this is used for determining the Earth's surface features. It is also used for setting out important works, important construction projects like dams and bridges. Okay, now obviously the accuracy of the triangulation figure will depend on accuracy of the final work will depend on the triangulation figures. Okay, so now what are these triangulation figures, or what do you mean by the triangulation system? There are three types of triangulation system. First order or primary triangulation, this is the highest order. Okay, this is usually employed to determine Earth's figure or to furnish the most precise control point to which the secondary triangulation stations will be connected. So if you are doing survey, the first thing that you will fix with the maximum precautions and maximum accuracy will be the first order primary triangulation stations. Okay, so average triangle closure, the error of closure, when you people must have done closed traverses, you know what is the error of closure. If your traverse doesn't close, okay, the closing point and the starting point, if it doesn't close, then that error is called error of closure. Okay, this should be in this case less than 1 second. Okay, then the maximum triangle not to increase more than 3 seconds. Length of the baseline will be around 5 to 15 kilometers. Then the length of the sides is supposed to be around 30 to 150 kilometers. Actual error of the base will be 1 in 3 lakhs, and the probable will be 1 in 10 lakhs. Discrepancy between two measures of a section is around 10 millimeters. Okay, and probable error of computed distance will be 1 in 60,000 to 1 in 2.5 lakhs, right?
Then probable error of astronomic azimuth is 0.5 seconds. Right. In case of secondary order triangulation stations, this will be the most precise ones I told you are primary, secondary will be coming after that. So first you establish primary stations and after that you establish the secondary. So the secondary stations will be having a closure error of around 3 seconds, maximum will be 8 seconds. In case of primary station, maximum was 3 seconds, right? Then the length of the baseline will be 1.5 to 5 kilometers, which was earlier started with 5 kilometers, goes up to 15 kilometers. Length of the sides is 18 to 65. Actual error of the base will be 1 in 1.5 lakhs, right? Then probable error will be 1 in 5 lakhs. Discrepancy between the two measures will be 20 mm. Then probable error of computed distance will be 1 in 20, what is this? 1 in 20,000 to 1 in 50,000. And probable error of azimuth is around 2 seconds. Then going to the third order tertiary triangulation, here the average triangular closure will be 6 and not more than 12. Baseline is around 0.5 to 3 kilometers. Length of the sides of triangles is 1.5 to 10 kilometers. Then actual error of base will be around 1 in 7.5 and probable error will be 1 in 25. Correct? And discrepancy will be around 25 mm. Probable error of computed distance will be 1 in 5,000 to 1 in 20,000. So this is not as accurate as the others. Let's have a comparison between the primary, secondary, and tertiary triangulation systems. So this goes in one go. Now the reference for this, this is a web resource. Okay, so what I have shown you previously and what is shown here, there may be a little bit of discrepancy, there may be a bit of error. Like for example, the length of the baseline from your textbook goes around 5 to 15 kilometers in the first order, but over here they are mentioning 8 to 12. But to give you a comparison, lengths of the baselines will be way more higher in case of the first order as compared to the third order. Lengths of the sides will be higher as compared to the third order. Average triangular error in this case is less than 1 second. So it's that accurate, right? Whereas in case of third order, it can be around 12 seconds. Okay, maximum error of closure is 3 seconds. Okay, actual error of base is 1 in 50,000. Probable error is 1 in 10 lakhs. Okay, here there is a discrepancy. Actual error of base as per your textbook is around 1 in 3 lakhs. Or anyway, here for the fifth one, this is inaccurate. Okay, don't take this. Take it on the previous part of your video. Okay, discrepancy between two measures. Okay, will be 5 mm. Okay, this textbook says is 10 mm. Alright, in any case, this is the comparison between the three types of systems to give you the precision in the three systems. Next is your triangulation figure system. Triangulation figure is basically a group of triangles, okay, which you will, it's kind of setting out of the points, like how do you select which points are going to be forming your triangles, okay. So the first one is a single chain triangle. You can see here the image, okay. Now single chain triangle, if this is going to be your setup or a selection of the points on ground, then what happens is it's very rapid, no doubt, but it will not be accurate because the spread is along one direction only. Okay, so this is okay if it's a narrow or strip of a terrain. So it's in a route survey. If it is a route survey, then this is fine. Okay, this will not be very accurate, so you cannot have primary work done with this kind of figure or this kind of a system of stations, right? Now, Double chain triangles, obviously this is way better than the first one. Okay, so this covers the greater area. In the third case, centered figures. You can see this. Okay, these are centered figures. So you have one point and you have surrounding 4 points. So this is obviously going to be way more accurate than the previous two. Okay, you can go, your spread is more, your coverage is more, it's more satisfactory, and this can be, this is more useful when especially your terrain is not very steep. If it's a flat terrain, then you go for this. Now, if you can see this, obviously this is going to take more time, because it's not that you have one point, the next point is in a line. So it's a wide way. It's covering the area in many directions, right? So this is going to be little slower. But the best one is quadrilateral. Now, in case of quadrilateral, corner stations and diagonal observations are forming the best figures. See, there is a lot of check that you get when you are setting up points in quadrilateral figure. This is suitable for hilly terrain. It's actually suitable for all the types of terrains. Okay, but mostly it is suitable for hilly terrain. Okay, and the computed sides can be carried by different combinations of sides. Meaning you have, you can calculate this particular side from this as well as this one. Let me tell you what I'm talking about. So if you have to calculate this side, you can do it by this as well as this, or this as well as this. So there are different ways of checking your work. The next thing is, how do you decide which type of figure do you select? So what is the criteria behind selecting the figures? Now, the figures should be so selected that there should be computation through at least 2 independent routes. So if you are doing any kind of measurements, there should be another set of measurements available to check this. Like in case of quadrilateral, I just told you, if you have, when you, let's say, set up these 4 points, okay, can you see this, right? I'm setting up this point, I can check, let's say, using these 2 distances, if I evaluate this one, okay, and if my figure is quadrilateral, I have these 2 also to have a check. Similarly, I have these 2 to confirm this. So the check should be possible. If you have a single-sided, the first one that we spoke about, the single chain triangles, this number of checks available will be limited. Figure should be such that at least one or preferably both the roots should be well-conditioned triangles. The word triangles is missing there. Now, what do you mean by well-conditioned triangles? It's a triangle which will give you, what do you say? It will give you a good, what do you say? It will give you a figure, let's say something like this. Okay? Something which will not give scope for error. Now, just imagine you have a point and you are setting it out from, this is your chain line, okay? And you are marking this point. Let's say this is your chain is 10 and this is your chain is 20. Okay? I tell you from chain is 10 at an angle of 60, the offset is 2 meters. And from chain is 20, at an angle of, let's say, 120, the chain is 2 meters. So you will be able to fix this point, correct? Now, in place of this arrangement, if I tell you from 10 meters, it is at an angle of 60, this point is at 2 meters, and from 11 meters at an angle of whatever, let's say 70, it is at. Now, will this be a right, well-conditioned triangle, something like this? Will you get a good fix? No, this point will not be a very good fix. To get a good fix, you need this point to be connected from 2 reference points. In such a way, these 2 reference points and this point together make a well-conditioned triangle. What is a well-conditioned triangle? I will go into that depth a bit later. Okay. after 1 minute. So all the points, the figures should be well-conditioned triangles.